All right, so I think everything is all right. Let's get moving. So Erskine discovers that the current causes magnetism, and Faraday discovers about 10 years later that using magnets you can also generate current. Catch is to vary the strength of the magnetic field inside the loop. There are two ways of doing it. Number one, you can move the magnet back and forth, so that's going to vary the strength of the magnetic field within the loop itself. So it's going to generate current. When the magnet moves forward, the current goes in one direction. When you put the magnet away, the current goes the other way. So the direction of the currents is alternating. And thus the concept of alternating current was introduced into physics. All right, so simply put, if you are varying the strength of the magnetic field inside the loop, that's going to give you current. That's the Faraday's law. All right, so that's one way of doing it. There's a second way of doing it. Second way is you just take this loop and then you spin it. In doing so, you change the area of the loop which is exposed to the magnetic field. All right, so there are two ways of doing it. So one way of doing it is you change the strength of the magnetic field, intercepted by the area of the loop, so that's going to induce current. The second way of doing it, you spin the loop. In doing so, you change the size of the area which is exposed to the magnetic field, so that's also going to induce current. So we will combine these two concepts into a single concept by introducing the concept of flux once again. So the flux represents the amount of magnetic field intercepted by the area of the loop. All right, so here's your vector dot product expressed in terms of a scalar. All right, so what's happening is the angle between the area vector, which is this, and then the magnetic field is changing when you're spinning the loop itself. Anyway, so if you vary the flux, it's going to induce current. That's one way of looking at it. And eventually we notice that the current is caused by the electromagnetic force. So, which means that the change in flux is going to induce an electromotive force, and electromotive force in turn is going to drive the current. All right, and then we introduce a negative sign in front of change in flux, indicating that the direction of the current is going to be such that its induced current is going to move in a direction which is going to oppose any change in flux. All right, so that's the reason why we got a negative sign there. So it's known as the lines law. So it says that the induced current will flow in a direction that's going to oppose any change in flux, in essence. All right, so that's the crux of what we covered this semester. Not this semester, last week, more like it. All right, so the purpose of the lines law is to figure out the direction of the induced current. All right, so when you move the magnet towards the loop, in essence, you're increasing the strength of the magnetic field intercepted by the area of the loop, so that the induced current is going to move in a direction that's going to oppose that change, that disturbance, that increase of the strength of the magnetic field. Right, so that is the lines law. So if you're increasing the strength of the magnetic field inside the loop, the current is going to move in a direction that's going to oppose that change. All right, so here's a different explanation for the same concept. So I'm increasing the strength of the magnetic field coming out of the page. So what the loop is going to do is there's going to be an induced current moving this direction, creating a magnetic field opposing this change. So the induced magnetic field is going to point into the page. For it to point into the page, it needs to be moving in the clockwise direction. If I reduce the strength of the magnetic field, intercepted by this area. This time, so I'm putting a negative here, meaning that I'm reducing the strength of the magnetic field. So that's what I'm doing. If that's the case, now the induced current is going to move in the opposite direction in order to generate a magnetic field, which is going to oppose this change. So that's our Lenz's law. So if you're increasing the strength of the magnetic field, induced current is going to move in a direction that's going to oppose that increase. If you're reducing the strength of the magnetic field, intercepted by the loop, the current, once again, is going to move in a direction that's going to oppose that change. So that's our lecture review. So the purpose of the Lenz's law is to determine the direction of the current. All right, so we got a loop. We're increasing the strength of the magnetic field coming out of the page. So which means that the current, so here's this strength of the magnetic field. The region is intercepting 4 magnetic field lines. Now we're increasing it from 4 to 5. So the current is going to move in a direction that's going to oppose that increase. So it's just going to move in the clockwise direction, or counterclockwise direction. So it's going into the page. Very good. In order to cancel out that change. All right. So obviously there are two ways we're generating current. Number one, you can literally vary the strength of the magnetic field inside the loop by moving the magnet back and forth. There's a second way of doing it. You can spin the coil inside a constant magnetic field. All right, so that's how you generate current. All right, so the current not only will change direction, and that's exactly what it's doing. It's going up and down. It's a sine wave, but also the value of the current is going to keep changing every single fraction of a second. All right, so mathematically, there are a couple of things that we need to focus on. So this is the coil that we were spinning. We are spinning the coil at this rate. F represents the frequency. In the United States, we use 60 hertz current, which means that the current changes direction 60 times per second, which means that this coil needs to be rotated 60 times per second. All right, so we're expressing this in terms of angular velocity or angular frequency, so I'll use the same term. All right, so the area vector, it keeps spinning relative to the magnetic field. All right, so the angle is going to keep changing relative to the magnetic field. All right, so in doing so, we end up changing the flux. So the magnetic field is going to stay the same. The area is going to stay the same. The only thing which is going to change is the angle. Angle is going to keep changing. All right, so a change in flux is going to generate an electromotive force. Whenever we're changing the flux, in essence, we're changing the angle. All right, so the angle can be expressed in terms of the rotational velocity and time. So that's what we're going to get to do. All right, so in essence, what we're doing is we're just changing the angle in time. So this becomes a time derivative. And then when you take the time derivative of this, you end up coming up with a mathematical expression. All right, so we're taking a time derivative of this. Just the cosine of omega t is going to be negative omega times sine of omega t. And so this expression becomes this expression, which means that the voltage is going to be going up and down, not only in direction as well as in value. And in our case, this is a sine wave that you got. So this represents the amplitude. Anything in front of sine is going to represent the amplitude. All right, so here's your sine wave, and anything in front of the sine wave is going to represent the amplitude. So you're looking at voltage, so this is going to represent the maximum voltage amplitude. So that's the peak value that's going to happen. So the maximum voltage amplitude or the peak voltage value is going to be related to the number of turns of the coil. It's going to be related to the strength of the magnetic field. It's going to be related to the area of the loop, and it's also going to be related to how fast you're spinning this. All right, I don't think this is on the formula sheet. Make sure if it's not, just put it on the formula sheet, so you're not fishing around for it. So that becomes the maximum voltage amplitude. All right, so it's the same thing. And the first one that you guys were looking at for college algebra, this is a more worked out version of the same concept using calculus. I should have used the second one. All right, so let's move forward. So the voltage is going up and down, but on average, you get zero voltage. So voltage is what drives current. So on average, you get zero current from the power. But if that's the case, what is it that we're paying for? All right, so we're not paying for the voltage. We're not paying for the current, in essence. We're paying for the power. Power company charges us for the average power that they provide. Okay, so what's the logic behind it? All right, so this represents the voltage that we're getting. So this is the maximum voltage, and it fluctuates up and down just like that. All right, in value as well as direction. And this is the current that the voltage generates or drives. So the current does the same thing. It goes up and down. So the average voltage is going to be zero. The average current is going to be zero. Average power is not. So now let's come up with a power expression. So power delivered or generated is your current times the voltage. Here's your variable current. Here's your variable voltage. All right. So this is the maximum current value. This is the maximum voltage value. All right. So sine omega t times sine omega t is going to be sine squared omega t. All right. So as soon as you square the sine, all right, we'll just stop at that point. You end up getting the power. All right. So the power is fluctuating between the maximum value and zero. All right, so they're not going to charge us for the maximum, and certainly not charge us for the minimum power that they're delivering. They will charge us for the average value. All right, so the average value is going to be 1/2 of the maximum value. All right, so this is your maximum current. This is your maximum voltage. So maximum current times maximum voltage is going to give you maximum power. If you divide it by 1/2, that's the average power that they're charging us, in essence. So the maximum voltage is voltage here, and the maximum current is not what they're charging us for. Obviously, they're not charging us for the minimum current either, which is not the way to do it. They're not charging us for the average. Let's just put it this way, because the real average is going to be 0. So they want to charge us, because if somebody says, "Oh, if on average, if I'm getting 0 amount of current, so what are you charging me for?" They want to be able to say, "Hey, listen, I'm charging you for the non-zero average current." So instead of saying non-zero average current, they usually talk about RMS, root mean square value of the current. In this case, all right. So 1 divided by square root of 2 times 1 divided by square root of 2 is going to be 1/2. So 1/2 can be divided into these two expressions. So you take the maximum current value, this was the voltage value, and divide by square root of 2, it's going to give you your RMS values. All right. So these are the non-zero averages for the current as well as the voltage that you're paying for. All right. So this is what I'm talking about. Square root of 1 divided by square root of 2 times square root of 2 is going to be 1/2. All right, so RMS value of the voltage that we get is 120. All right, so this is the non-zero average. This is what you're paying for. The maximum value is going to be 170 volts. All right, so that's what we got. All right, so when you spin a coil in a constant magnetic field, you're changing flux. Changing flux is what generates current. All right, so the faster you spin it, the larger the electromotive force is, the bigger the electromotive force is, the bigger the current is. So the relationship between the maximum electromotive force and the frequency of the spin is a direct one. Right, so this is the maximum electromotive force, is the maximum voltage amplitude. That's your peak voltage. So it depends on the number of turns, strength of the magnetic field, area of the loop, and how fast you spin it, meaning the frequency of the spin. So in the United States, it's going to be 60 hertz. All right, so we talked about the non-root, we talked about the root mean square value that represents the non-zero averages. All right, so the motional electromotive force is related to the motion of a conductor through a constant magnetic field region. Or it doesn't need to be a constant magnetic field region. It's just that if you're dragging or driving or pushing any sort of conductor through a magnetic field, what's going to happen is there's going to be a charge separation. All right, so positive charges will go one way, the negative charges will go the other way. So when there's a charge separation, there's going to be an electric field within that separation distance. So all of a sudden, that region is going to become energized, which means that it's going to become a battery. All right, so the question is, what's causing this charge separation in this region? So if you focus on the positive charges, if you focus on a single positive charge, when the conductor is moving in this direction, the charge is moving in that direction inside the magnetic field. So the magnetic field is pointing into the page, and the charge is moving to my right, which means that there's going to be a magnetic force acting on a positive charge and charges. So these positive charges will start to move in the opposite direction. Negative charges will move in the opposite direction. And all of a sudden you get a charge separation. All right, so when one region becomes positively charged, the other region becomes negatively charged. This region becomes a positive terminal, this becomes a negative terminal. Obviously, there's going to be an electric field pointing in the downward direction through this separation distance. So electric field has energy stored in it, which is known as voltage or potential. So there's a potential difference created within this. So, which means that this conductor is going to act like a battery because of its motion. All right. I didn't put too much emphasis on the derivation last night. I'm going to put a little bit of emphasis on the derivation because I'm thinking that there's going to be an extra credit problem that's going to require you to be able to do this sort of stuff. All right, so number one, the charges will separate until the strength of the magnetic field is the same as the strength of the electric field. Right, so as this thing is moving, so there's going to be a charge separation within that region. So the magnetic field is pointing into the page. All right, so the velocity in this direction. So there's going to be a force in the upward direction for positive charges. For negative charges, the force is going to be in the downward direction. So the charges will separate. And there's an electric field pointing in the downward direction, which is this. And there's a separation distance. So the combination of the electric field and separation distance is going to give us the voltage difference within this region. All right, so it's going to give us the voltage difference within that region. Okay, just waiting for this die off. All right. All right, so and then we will start the derivation. So the electric field acting on the charges is going to induce an electrostatic force. And the charges moving inside the magnetic field. All right, so this is the component of the velocity vector that's going to be perpendicular to the magnetic field. That's what it means. So the charges will separate until the electric strength of the electric field is the same as the strength of the magnet. The strength of the electrostatic force is the same as the strength of the magnetic force. All right, so the electrons will cancel. So the charge is going to cancel. We end up getting this interesting relationship between the strength of the electric field and the magnetic field. There's something here that we will explore in the future within a few weeks regarding the magnitudes of the electric and magnetic fields and how it's related to the speed, in this case, of the conductor. All right, and in order to get the voltage difference between the charge regions for the electromotive force, the only thing we have to do is multiply both sides by the length of the conductor. So both sides will get multiplied by L, in essence. And then if you multiply both sides by L, this side is going to give you the electromotive force, and this side is going to be, all right, so if you multiply both sides by L, we can skip this step. This is going to give you this, all right, because E times L is going to be the electromotive force. All right, so it's the electromotive force, the amount of electromotive force that you generate is going to depend on how fast this conductor is moving inside this magnetic field. It also depends on the length of it. Okay, so instead of saying the perpendicular component of the electromotive force, what we do usually is we express this in terms of a dot product. So it's going to be V bar dot B bar times L. That's the way we would express it. So more generalized expression than I want you guys to use is this one. Okay, so no, this is not a dot product if that's the case. So this is going to be a cross product. All right, guys, when you see this, just use this. That's what I'm getting. So that's a cross product. You will have a test question regarding this. In fact, the problem that you will be solving on the test, short work problem, is going to be related to this. All right, this is an extension of everything that we covered, except what we'll do is we'll take the loop out of the picture. Okay, so if you are varying the, okay, so we got this region within which we're varying the strength of the magnetic field. So what happens when you vary the strength of the magnetic field within? All right, so there are no wires, there are no loops. Only thing we got is the field, and we're just varying the strength of the magnetic field. So what should happen is when you start to vary the strength of the magnetic field within that region, it should cause a circulating electric field, in essence. All right, so when you increase the strength of the magnetic field within that region, the electric field is going to circle one way. When you reduce the strength of the magnetic field, the electric field is going to circle the other way, in essence. All right, in this case, we are just reducing the strength of the magnetic field, so the electric field is circling this way. And if you increase the strength of the magnetic field, the electric field is going to circle the other way. Okay, so question is, how do we even know this? Okay, so that's what we were discussing. All right, so how do we even know this? The reason why we know this is the following. Look, change of flux creates an electromotive force, and electromotive force in turn is what drives current. All right, so this is electromotive force inside the loop, within the electromotive force in the wire of the loop is going to drive current. All right, so here's the area of the loop. I'm varying the strength of the magnetic field within that loop. That's your Faraday's law. And by varying the strength of the magnetic field inside this area, I'm changing the flux. And that in turn is creating an electromotive force. And then now let's get back to the concept of the electromotive force, which happens to be the same as voltage, and voltage is related to the strength of the electric field through a separation distance R between two opposite charge regions. Okay, this is the way we were dealing with. All right, so the electromotive force is the same as voltage and voltage difference, which is the amount of energy stored within this region, is going to depend on the strength of the electric field within the spacing of this distance. So the spacing of this distance is the separation distance between two opposite charge regions. All right, so the same idea implies here. So this R that you're looking at, the separation distance, becomes the total length of this wire. In essence, this is the total length of this wire is going to be the circumference of this wire. In essence, what's happening is when you vary the strength of the magnetic field, it's causing some kind of an electromotive force. In a sense, it's causing a circulating voltage here along the way. Okay, here everything is static, but here it's not. There's a circulating current which is being pushed in this direction. There's a circulating voltage, electromotive force. That's what it means. And the reason why there's a circulating voltage is because, look, the voltage is caused by the electric field, because the voltage represents the amount of energy stored inside the electric field within this distance, within this gap. In essence, it's giving you a circulating voltage, and the circulating voltage comes about because of the circulating electric field along this line. All right, so electric field acting on the charge is causing a circulating force. So you end up getting this circulating force, and that's in essence what's driving. All right, so this everything that I expressed is signified here. So there's an electric field in this circular direction, all right, which is responsible for a circulating electromotive force. And this comes about because you're changing the flux within this region. All right, so we add an extra component here. So how does that go? All right, so the summary statement is when you vary the strength, when you vary the flux within this region, and in this case, I'm just varying the strength of the magnetic field within this region. Inside this constant area, I'm creating an electromotive force. And the electromotive force is coming about because I'm creating a circulating electric field within this region. So this is the electric field. It's always pointing in the direction of, if you're using a dot product, on the direction of S. S is going to be your arc length in essence, okay, along this curvature. So this electric field, the component of the electric field responsible for the current is the component which is along the direction of the curvature of the wire. That's what it means mathematically. So this is what causes that, in essence. All right, so that's the concept. So there's going to be a problem related to this. So my recommendation is you guys practice the following problem. We just move on to the next page. So problem number 6 is the one that I recommend that you guys practice. It's not a difficult, mathematically, this stuff is not difficult. Conceptually, make sure that you make all these connections between the electromotive force, the electric field, the current, and everything else. All right, so this is problem number 6. All right, so this capital R is the region, radius of the region, within which we will change the strength of the magnetic field. All right. So the capital R is the radius of the region within which we will change the strength of the magnetic field. So the flux is going to change within this yellow region. All right, so if you're changing the flux within this region, it's going to cause a circulating electric field. All right, so there's going to be circulating electric field within this region, outside of this region, and so forth. All right, so in this particular problem, we're changing the magnetic flux at this rate. So the strength of the magnetic field is changing within this region. And then we're interested in the magnitude of the induced electric field within this region. All right, so the region has a radius which is 8.5 centimeters. And within that 8.5 centimeters, we want to know the strength of the circulating electric field at this distance. And then we will also be interested in the strength of the electric field outside of this region, circulating electric field outside of that region. All right, so that's the formula that we will start off with. All right, so when you vary the strength of the magnetic field, focus on this portion. This is the area of the region where we're varying the strength of the magnetic field. All right, and this is our circulating electric field within that region. All right, so we're varying the strength of the magnetic field within this region, and then we end up getting a circulating electric field. And then we will integrate everything in the counterclockwise direction. So this is the direction that the electric field circulated. So the first thing we do is we're looking at the strength of the circulating electric field within the region of the change in flux. Right, so the radius is the radius of the region of change in flux that you're looking at. All right. So this circulating electric field is going to come about because of change in flux within the smaller radius, not outside of it, but within the region, inside the radius of this region where the electric field is going to be circulating. So when you get to this A that you're looking at, this A represents the region within which the flux is changing. And so the only region which is going to be responsible for the circulating electric field is the area of the region which is within the circulating electric field, area circulating electric field. So this A that you're looking at